Well, hello, ladies and gentlemen. So last time we finished a simple example involving calculating the physical properties in terms of composition of a mixture. So today we're going to go on to ideal gas mixtures. We're going to define an ideal gas mixture. Basically, an ideal gas mixture is a mixture or a combination of two components or more components. The mixture itself behaves according to the ideal gas law, and each component behaves according to the ideal gas law. So both the components of the mixture and the mixture itself behave as an ideal gas. That's basically the definition of an ideal gas mixture. Then we're going to move on and look at partial pressures and volumes. So we're going to define partial pressures and volumes. And then we're going to look at Dalton's law of partial pressure, Amagat's law of partial volume. So introduce these conservation laws for partial pressure and volume. Then we'll go through and state the formula for, or derive it, we'll see if we have time. We'll state the formula for the gas constant for an ideal gas mixture. And then we'll talk about how to apply energy and entropy balances to mixtures of gases. Instead of a pure substance, now we have mixtures. Basically, it's just the same old energy and entropy balance, but we sum over all components within the mixture. So there's an extra summation sign in the mass or mole transfer of energy or entropy. So you have to modify the energy and entropy balance just a little bit. And then we'll see how far we get on an example involving an open system where we mix two different ideal gas components together. Okay, that's the plan for today. So let's go over the definition of ideal gas mixture. Ideal gas mixture. So what's the definition of an ideal gas mixture? Well, we have this tank full of various components. So blue is one component made out of some chemical, and the white is some other chemical component of a mixture. And this mixture here overall has a mixture temperature, a mixture pressure. So if we have a pressure gauge here. So if we have a pressure gauge here. So we have a P mix, mixture pressure, mixture temperature, a mixture volume, a mixture volume. And the idea here is that the mixture obeys the ideal gas law. So P mix, V mix is equal to the gas constant for the mixture times the mass of the mixture times the temperature of the mixture. We can also write this in terms of moles. So we can also say RU N mix T mix. So the mixture behaves as an ideal gas, where the mixture has a certain pressure, temperature, volume. There's a certain amount of the mixture, whether it's in kilograms or in kilomoles. And so the mixture behaves as an ideal gas. So that's the first requirement. The second requirement, we'll talk about this in a moment, is that each component, each chemical component also behaves as an ideal gas. So this is for the mixture. So mix obeys IGB. But we also have that each component obeys the ideal gas law. So we also have, so each component is referred to as the ith component. So we also have pressure of the ith component is equal to pressure times the pressure of the ith component times the volume of the component, well, times the volume is equal to the mass of component I times the gas constant for component I times temperature of the mixture. And this volume is also the volume of the mixture. So each component obeys this equation here. The partial pressure or component pressure, P sub I times the volume of the mixture, is equal to the component mass times the gas constant times the mixture temperature. Why am I not putting the component temperature here, and why am I not putting the component volume there? Why do I have B mix and T mix? Well, notice that the mixture, each component has the same temperature in the container and takes up the same amount of volume. I could put VI here, I could put TI, but what I really mean is V mixture and T mixture because they take up the same amount. Each component takes up the same amount of space in the mixture and it all has the same temperature. There's also another equation here, another version of this ideal gas law for each component. There's also one that says P mix times the component volume VI is equal to MI RI T mix. Okay? So these two equations here are obeyed by each component I. Each component or chemical, if you like, in the mixture, each component I obeys IGB. Okay? Well, that's the definition of an ideal gas mixture. Ideal gas mixture. Okay, let's get into a little bit more detail here on what these P sub i's and V sub i's refer to in the component IGB equation. I think it's pretty clear that the mixture clearly obeys the ideal gas law if it's an ideal gas mixture. But what is this PI and VI all about? These are called partial pressures and partial volumes. We're going to talk about these right now. Okay? So let's look at partial pressure. What is partial pressure? So what's partial pressure? Let's say we have a mixture here in a tank, and I have a little pressure gauge at the top. So here's my pressure gauge. Okay? And initially I have some bunch of different chemicals in here. I'm just going to put two different chemicals. It doesn't matter. Two different chemicals in here, two components. Can generalize to n components, who cares? So right now we have a mixture. So the mixture has a certain volume, it has a certain temperature, and it also has a pressure, okay? Now what I'm going to do is I'm going to take a little atomic or molecular tweezer and remove all the white components here, the white atoms or white molecules. Could do the blue, who cares? I'm going to remove everything but one component. So I'm going to get rid of all the white molecules. All the white molecules. So now I'm going to remove all of them and I get just blue. The blue molecules are all that left over. Notice the volume taken up by the blue molecules is still V mix. It still has a temperature T mix. But now, of course, there's a certain mass of component I. The component I is my blue component. So I equals blue component. Okay, I'm looking at the ith component here, okay? There's also a certain number of moles of I as well, okay? Now, if I measure the pressure, I no longer am at P mix, I'm at some lower pressure. I'm at some lower pressure. And this pressure measured at the pressure gauge of the tank, only containing the leftover blue components or molecules, is my partial pressure. So here's my P sub I. P sub I is the component pressure, component or partial pressure. P sub I is called the component or the partial pressure. And the partial pressure obeys the ideal gas law if it's an ideal gas mixture. So note, P sub I V mix is equal to M sub I Ri T mix. Okay? All right? Now I can also write this here. Maybe I should write it. I can write it in one of two ways. So I can write this as Mi Ri mix, or I can write it as Ni Ru mix. Okay? All right. How do we calculate the partial pressure of some component in a mixture? How do we get the partial pressure of some component in a mixture? Well, that's actually pretty easy. First of all, let's solve for, I'll tell you what, let's divide. Let me write this second version right here. So I'm going to write Pi V mix equals Ni Ru T mix. And what I'm going to do is I'm going to divide by the ideal gas law for the mixture. So I'm going to divide that by P mix, V mix, N mix, Ru T mix. Let's just divide the ideal gas law for the component by the ideal gas law for the mixture. Notice that the V mixes cancel out, the RUs and the T mixes cancel out, and I get the partial pressure of component I divided by the mixture pressure is equal to the number of moles of component of I divided by the number of moles in the mixture. Now, Ni divided by N mix is the mole fraction of the component I. So this is Y sub I here. This is the mole fraction. In other words, P sub I is equal to P mix times the mole fraction of component I. So that's how you get the partial pressure. So this P sub I right here is equal to the mole fraction times the original mixture pressure. That's what the P sub I is equal to. Okay, so let's write this up here. The partial pressure, P sub I, is equal to the mole fraction times P mix. Okay? Now, one thing I want to point out to you is that the sum of the partial pressures of all the components in the mixture is equal to the mixture pressure. So if I sum up all the P sub I's, I should get P mix. Well, let's see if that's true. The sum of the partial pressures is equal to the sum of the mole fractions times the mixture pressure. Well, the mixture pressure is a constant in the summation, so I can factor that out. And so I get P mix times the sum of the mole fractions, and we know that the sum of the mole fractions is equal to 1 over all components. Okay? So we have what's called Dalton's law. P mix is equal to the sum of the partial pressures of all components. So this is called Dalton's law of partial pressure. Dalton's law of partial pressure. The sum of all partial pressures summed over all components, of all the partial pressures, is equal to the mixture pressure. So make sure that you have boxed up somewhere the expression for the component pressure, the partial pressure, and you also have Dalton's law boxed up in your notes somewhere as well, okay? So we also have P mix is equal to the sum of the partial pressures. Okay, let's make sure we have that boxed up somewhere. Okay. Okay, let's do another law here called Amagat's law of partial volumes. Let's do the same experiment, but I'm going to run it. Instead of running it in a rigid tank, I'm going to run it in a piston cylinder device and keep the pressure constant in my mixture as I pick out all but one component. Okay. So now I'm going to have a piston cylinder device. So now we're going to talk about partial volumes. Partial volumes. What's partial volumes about? V sub I. What's that about? Well, let's say we have a piston cylinder device. Okay? And this thing, some force is applied to this piston. And the pressure is kept constant in this piston, on this piston, and therefore in the piston cylinder device. So now I have my two components in here. So I got two components. I could have n components, who cares? And of course I measure the pressure here. So here's my pressure. So my pressure right now is P mix, and my temperature is T mix. My volume is V mix. Okay? All right? And of course, I have a certain number of moles, N mix, and a certain mass, N mix, but I'm not going to write that down. Okay, so I'm going to keep pressure constant. Isobaric process. So I'm going to remove all of the white material, the white components, keeping pressure constant. So I'm going to remove all the white components, leaving only the blue chemical or component. And of course, as I do that, keeping pressure constant, volume is going to shrink. So I remove all the white component. I'm only left with the blue. Okay, so pressure here is still P mix. I still have pressure P mix. This is an isobaric process. But now I have a much smaller volume. I now have the partial volume V sub I for the component. Okay, I have a partial volume V sub I. I'm still at a temperature T mix. And of course, I have a certain number of moles in there, N sub I, as well as M sub I. Okay, there's nothing in there but component I. So I is the blue component. I is blue component. All right. And these temperatures, pressures, and mixture and component volumes are represented by the equation as follows. P mix times the component volume for element or component I is equal to, and I got two versions here. I have MI, RI, T mix, and I have NiRu T mix. Okay? So each component obeys the ideal gas law, and in this case, the V sub I refers to the component volume. Component volume. How do I calculate the component volume, V sub I? How do I do that? Well, let me take the second equation here. P mix V sub I equals N sub I Ru T mix, and I'm going to again divide this equation by the ideal gas law applied to the mixture. So I get P mix, V mix, N mix, Ru T mix. And of course, the temperatures, the gas constant, and the pressures cancel out. And we'll get a similar expression here as we got for partial pressure. We have that the mixture component volume, V sub I, is equal to V mix times the mole fraction for component I. Okay? So the component volume is equal to the mole fraction times the volume mixture. I'm going to put that back over here. So we have V sub I is equal to Y sub I V mix. Okay, put a box around that. Needless to say, the sum of the component volumes, needless to say, if I were to sum up the component volumes, I would get V mix times the sum of the mole fraction, which of course is equal to V mix because the sum of the mole fraction is equal to 1. So I would get a similar law here. I would get V mix is equal to the sum of the component volumes. Okay? By the way, this last quantity here, so this is Dalton's law of partial pressure. This here is called Amagat's law of partial volume. The sum of V sub I is equal to V mix, and this is called Amagat's. Amagat's. Amagats. Amagat's law of partial volumes. Okay, you just do it by summing up the partial volumes, and that's what you get. Okay. Okay. Now let's talk just a little bit more about the mixture and what this entails, what all these laws imply. What all these laws imply. So sorry. Sum of the partial volumes is equal to the volume mixture, Amagat's law. Amagat's law. So let's say you want to calculate, you've got some mixture here. Got some mixture. So here's some mixture, ideal gas mixture, again composed of various components. Various components. Okay. Do I have any other colors? Ah, here we go. All these different components. And this mixture has a certain volume, a certain pressure, a certain temperature, and a certain amount of mass and mix. Okay? And let's say we want to determine the gas constant, R, for the mixture. So I want to be able to predict or relate pressures, temperatures, and volumes for the ideal gas law. So we're going to look at ideal gas constant, mixture, constant. So I want to calculate R mix. That's what I want to do. That's what I want to do. Okay? Actually, let me, I'm going to break it right here. So I want to calculate the gas constant for the mixture. So let me write the ideal gas law applied to the mixture. So I have P mix, V mix is equal to M mix, R mix, T mix. Now I can solve then for the gas constant R mix. And that's equal to what? It's equal to P mix, V mix, divided by the divided by mass of the mixture times T mix. So the mixture obeys the ideal gas law. Mixture obeys the ideal gas law. Now note that the mixture pressure according to Dalton's law is the sum of the partial pressures. So this is the sum of the partial pressures of each component. Okay? So this is equal to the sum of P sub I times V mix over M mix T mix. Now remember, according to the ideal gas mixture, each component obeys the ideal gas law. So the partial pressure P sub I is equal to M sub I, R sub I, T mix, divided by V mix. Okay, each component obeys the ideal gas law. All right? So what have I got here? I'm going to put this in the summation. Notice that V mix and T mix are constants, so they come out of the summation. So I get T mix over V mix. And then I have the summation of M sub I, R sub I. Okay? And then I have M mix and T mix in the denominator. And I have V mix left over in the numerator. Okay, I just made the substitution for the ideal gas law for the component. The T mix, the V mix cancel out. And I get the sum of the mass of component I times its gas constant divided by M mix is equal to the gas constant for the mixture, okay? Now, M mix is constant. M mix is constant, so I can pull it into the summation. And I get the sum of the component mass divided by the total mixture mass times the gas constant for the ith component. Now, Mi over M mix is equal to the mass fraction of the component I. So this whole thing is equal to the sum of the mass component I times the gas constant I summed over all components in the mixture. Okay? So we have the mixture gas constant is equal to the sum of the mass fractions times the gas constant for the mixture summed over all components. So let me put this down here. R mix is equal to the sum of the mass fraction times the component gas fraction summed over all components. That's how you calculate the gas constant for the mixture. Okay? How do we get other properties besides the gas constant for this mixture? How do we get other properties? How do we get the internal energy of the mixture? How do we get the entropy of the mixture? The enthalpy of the mixture? How do we get any property for the mixture? Well, note, for property extensive, extensive property beta, you've seen this before. Remember the Reynolds transport theorem? For the extensive property beta, beta for the mixture is equal to the sum of the mass of mixture I, component I, times the specific beta for I summed over all components. For example, U mix is equal to the sum of the mass of each component times the specific internal energy of each component, summed over all components. Enthalpy, same thing. H mix is equal to the sum of the mass of each component times the specific enthalpy for each component. Same thing for entropy. S mix is equal to the sum of the mass of each component times the specific entropy of each component, summed over all components. Very easy to calculate mixture properties. You just sum up the property for each component, just sum them all up. We can also write this in terms of moles. We can say the sum of the number of moles of component I times B bar. That would be on a per mole basis. So this B bar is per kilomole, not per kilogram. That's what the bar is about. Okay? So I can also calculate the internal energy, enthalpy, and entropy of the mixture as sum of N sub I, U bar sub I, summed over all components, and the sum of N sub I, H sub I bar, summed over all components, and same thing with specific entropy, same thing with entropy. Oops. N sub I, S bar sub I. So I just sum up the specific, sum up the entropy, enthalpy, internal energy of each component, and I get the total mixture, internal energy, enthalpy, and entropy. Okay? So use these equations here. So I'm going to write this right down here. So beta mix is equal to the sum of the mass of component I times B sub I summed over all components, or the sum of N sub I B bar sub I summed over all components. So that's how you calculate properties of the mixture, like internal energy, internal energy, entropy, and enthalpy. So in this case, beta equals H, U, and S of the mixture, okay? So why don't you box that one up too? Okay? The total energy, enthalpy, and entropy of the mixture is that of the components summed up. That is all that says. That is all that says. Okay, so what does that entail for the energy balance, in particular the energy balance for an open system? For a closed system, you can just, so in the closed system, let's write our energy balance for a closed and open system, and I'll show you how they're a bit different compared to a single component system, no mixtures. So E balance for mixtures. So we have our closed system mixture that undergoes some process. So this is some mixture. So go from state 1 to state 2. So there's a bunch of stuff in here. It's undergoing some kind of process. There's some heat interactions, there's some mass, there's some heat interactions, maybe some work interactions, who knows? So this thing, we could be adding heat to it from 1 to 2, or it could be doing work from 1 to 2. The energy balance is just the same as for our single component, pure substance that we've been working with up to this point in the semester. So the E balance simply says Q minus W is equal to delta E for the mixture. And this is all from state 1 to 2. Okay, to get E for the mixture, you simply sum up the component total energies. So E for the mixture is the sum of either MI, EI, or the sum of NI, E bar I, okay? Usually total energy, specific energy is going to be internal energy. So you could put U's up there and I guess it would make more sense, okay? All you got to do is be able to calculate the total mixture energy before and after, and boom, you can use your first law as you normally do, okay? So this is for a closed system. How about for an open system? So let's say we have an open system here, and I have some ports with different mixture components flowing in, So I have M dot I, dem dot 1, and also N dot 1. And then I have N dot 2, M dot 2, different gases here. So one component flows in at this port, another component flows in at this port. And I got a bunch of components and I all the way end up down at N dot, I don't know, I max and M dot I max. So I'm mixing I max components together or something, okay? And then maybe at the outlet, I have some components coming out too. Who knows? Who knows? I have a bunch of components coming out. Different species or components, okay? So I have M dot I, N dot I, all the way down to however many components I have leaving the control volume. So this is my open system. Maybe I have some work going on, W dot, who knows? Maybe I'm adding heat, who knows? I don't know, who knows? So what's the energy balance applied to that system there? What's the energy balance? Well, it's the same old energy balance that we're used to, except we have to take into account the fact that we can have multiple chemical components. So the E balance for open system is Q dot minus W dot is equal to the time rate of change of energy within our control volume plus the sum, double sum over all species, sum over all outlets of M dot I, HI, KEI plus PEI, summed over all components. So a double sum here, summed over all components I, summed over all outlets. The total energy flow out due to all components. So we have this extra sum. So this is the component sum over all components. This is the outlet sum over all outlets, minus the same thing summed over all inlets. M dot I, HI, KEI, PEI, summed over all components, summed over all inlets. Component, sum, inlets, sum. Okay? If we had one chemical species, if we had one component, this second summation would go away and we would have one chemical compound, and I would revert back to sum over all outlets, M dot H plus KE plus PE. That's what I would have, okay? Now you can also write this in terms of mole fractions. So for example, you can also write this in terms of mole flow rates. I can use H bar, KE bar, PE bar, and N dot there. I can also do this. Sum over all outlets, sum over all components, N dot I, H bar I, plus KE bar I, plus PE bar I. I can also do this, okay? Same thing with the inlet term. If you notice, this is quite advantageous because some of the table's properties, as you recall, are on a per unit mole basis. So let's have a look here. Okay. So if you recall, so here's our H2O properties. Here's our air properties, and we also have B12 IGB ideal gas properties for selected gases. We have CO2, carbon monoxide, H2O, oxygen, and nitrogen. And notice these are overbarred quantities, kilojoule per kilomole, kilojoule per kilomole degree in Kelvin. So sometimes it's easier to do problems knowing the mole flow rate as opposed to the mass flow rate. You can immediately go to the tables and extract out specific properties for each component. Okay? Okay, let's take a break for a second here and we'll do an example involving an energy balance on an open system so that we are all pretty clear what to do. Okay, so let's do a problem here. We have an adiabatic isobaric mixing chamber that you see right here. At inlet port number 1, we have ethane, which is C2H6 flowing in. And the ethane, which is in port number 1, has a temperature of 20 degrees C. At port number 2, we have methane, CH4, flowing in at a temperature TCH4 at port number 2 of 45 degrees C. So the ethane and the methane flow in at different temperatures. The mass flow rate for the ethane is 9 kilograms per second, and the mass flow rate for the methane is 5 kilograms per second. So we have two components, two different chemical components with different temperatures, different flow rates. They flow into this adiabatic mixture. So I'm going to tell you right now, it's an adiabatic mixture. What that means is the pressure of the ethane, the pressure of the methane, and the pressure of the mixture. So these two components mixed together are all the same. The pressures are all the same. And we end up with an outlet flow rate of m dot mix and an outlet temperature for the mixture T mix. So what are we going to find here? Let's find the exit temperature T mix. Let's find out what the temperature of this mixture is when it emerges on the right-hand side. Now, one little thing here, we're going to assume constant specific heats. The specific heat for the ethane, C2H6, is 1.766 kilograms per kilojoule per kilogram degree in Kelvin. Oops. And the specific heat, oh, now I got to find it here, for the methane. I'm sorry, CH4 for the methane. The flow rate for the methane is 2.254 kilojoules per kilogram degree in Kelvin, okay? Actually, I just realized this flow rate for the methane, this is actually 4.5 kilograms per second, not 5. So 4.5, my fault. 4.5 kilograms per second for the methane, 9 kilograms per second for the ethane, okay? And I want to calculate the final mixture temperature. Okay, let's apply the energy balance for my open system. Just like before, except now we have a mixture. So we're going to have to take into account that there's some different species here, different components in my flowing through my various ports. So let's apply the energy balance. So we have Q dot minus W dot is equal to dE CV dt. Change of energy within my control volume over time. I'm going to assume it's steady state here in a minute, so that term is going to go away. And then I have a double sum plus the double sum, summed over all outlets, summed over all species I, m dot hi plus PEI plus KEI, summed over all species, summed over all outlets. And then I have minus double sum, summed over all inlets, sum over all species, m dot I, HI plus PEI plus KEI, summed over all inlets. Okay, so this is the energy balance applied for multiple components. Multiple components. Note the double sum. Take into account the fact that we have multiple chemical species. If it was a single species problem, a single chemical component, this second sum would go away and the m dot I would just become an m dot and the i's would go away and we'd get back to our old single component energy balance. Okay, so let's see if we can whittle this thing away. We're told that it's so I tell you it's an isobaric adiabatic mixing of methane and ethane. Notice that there's no propellers in here, so there's no work interactions going on. There's no heat interaction going on, and I'm also going to assume steady state. So the dECV dt is going to go away. 0, 0, 0. Okay, so for my assumptions, I'm going to write steady state here. Steady state. And W dot equals 0. No work interaction, steady state, okay? I think I'm also going to make my life really easy. I don't have any information about the change in potential or kinetic energy of any of the components, gases, at the inlet or the outlet. Inlets or the outlets. So I'm going to ignore these. Ignore the kinetic and potential energy terms. No change in kinetic, negligible change in kinetic and potential energy for each component. So I'm going to say delta PE for the ith component is equal to delta KE for the ith component, and I'm going to set them equal to 0. So they go away in the energy balance, okay? Okay, so let's write what we have left. At the outlet, I have 2 species flowing through. At the outlet, I have 2 species, 2 components. At the outlet, I have CH4 plus C2H6. I have ethane and methane together to form a mixture. So I will have 2 M dots at the exit. Now note that there are no chemical reactions going on here, so there's no M dot ethane being converted into ethane. There's no species or components disappearing. So I'm going to write down here as an assumption, no chemical reactions. So what that means is M dot I in equals M dot I out. I'm not converting, I'm not burning methane or converting methane into ethane. I'm not producing any, there's nothing chemical going on here, it's just mixing. So the mass flow rates for each component at the inlet and the outlets must be the same, okay? Summed over all inlets versus the outlet must be the same, okay? Okay, so let's attack the summations here. At the outlet, I have 2 chemical components. I have the methane and the ethane. So at the outlet, I have M dot CH4 times the specific enthalpy of the CH4 at the outlet. And the outlet is location 3. The outlet is location 3. So this would be H evaluated at location number 3. So I got the ethane as well, so I also have plus M dot C2H6 H C2H6 evaluated at the outlet. The outlet has a certain temperature, therefore the outlet methane and ethane enthalpies, specific enthalpies will have a certain value, okay? So I got 1 outlet and 2 chemical components with the associated enthalpy flows at the outlet. At the inlet, I've got the opposite. I've got 2 inlets, and the components are not mixed at the inlet. I got 2 inlets, one at location 1, one at location 2. The ethane's at 1, the methane's at 2. They are not mixed. They are not mixed, but I have 2 inlets. So this second term here is M dot C2H6 H C2H6 at the inlet, and the inlet port for the ethane is port number 1. Port number 1 is where the ethane comes in, okay? And port number 2 is where the methane comes in. So I'm going to add on the enthalpy flow for the methane. CH4, HCH4 evaluated at inlet port number 2. Okay? So what do we have here? Notice these mass flow rates for the ethane and the methane are the same. So I'm going to group together terms. 0 equals m dot C2H6. And then I have H C2H6 evaluated at the outlet, location 3, minus H C2H6 evaluated at the inlet port, location 1, plus m dot CH4, H of CH4 evaluated at the inlet, its inlet, which, I'm sorry, outlet, which is port number 3, plus H CH4 evaluated at the inlet, which is port number 2. Okay? Now I can also rewrite this in terms of a delta H. So this is m dot C2H6 delta H C2H6 from 1, 2, 3 plus m dot CH4 delta H CH4 from 2 to 3. Now, I'm assuming constant specific heat, so this delta H is equal to Cp delta T. So this guy right here, this is Cp of the C2H6 times temperature T3 minus T1. And this guy right here is Cp of the CH4 times temperature T3 minus T2. Okay? T1 is the ethane inlet temperature, and T2 is the methane inlet temperature. Okay, so let's write out what we have. Let's write out what we have here. Let's write out what we have. So this is all equal to 0. So this implies, I guess I'll get rid of this too. So this implies 0 equals m dot C2H6 Cp for the C2H6 T3 minus T1 plus m dot CH4 Cp CH4 T3 minus T2. Okay? Now, in the problem statement, I have the mass flow rates for the various components, the specific heats, and I also have the temperature. Let's see here. TC2H6 at port number 1 is just my T1, and TCH4, i.e. at port number 2, is my T2. So I have T1 and I have T2. I have the m dots, I have the specific heats. So I got one equation, and one unknown. T3 is my unknown. Let's solve for the outlet temperature, T3, or my mixture temperature if you like. So let's see here. T3 is equal to, oh boy, let's see here. So T3 is equal to m dot C2H6 Cp C2H6 times T1 plus m dot CH4 Cp CH4 T2, and all of that is divided by m dot Cp m dot C2H6 Cp C2H6 plus m dot CH4 Cp CH4. And let's plug in here. Let's see here. My m dots are 9 and 5 kilograms per second. And the temperature is 20 degrees C and 45 degrees C. So let's see here. Make sure I get this right. 9 kilograms per second for the ethane. 9 kilograms per second for the ethane. The Cp for the ethane, 1.766. 1.766 kilojoules per kilogram degree in Kelvin. And then I have temperature T1. It doesn't matter whether I write it in Kelvin or not, because it involves a temperature difference. I get 20 degrees C. And then I have 5 kilograms per second times 2.254 kilojoules per kilogram degree in Kelvin, 2.254 kilojoules per kilogram degree in Kelvin. And the temperature of the methane coming in is 45 degrees C. Again, it doesn't matter whether I do this in Kelvin or centigrade, because notice I have a temperature difference here. As long as I write these temperatures all in the same units, it doesn't matter whether I use centigrade or Kelvin, because the 273 cancels out in the difference here, okay? Cancels out in the difference here. So now I have 9 kilograms per second, 1.766 kilojoules per kilogram degree in Kelvin, plus 5 kilograms per second. And then I got 2.254 kilojoule per kilogram degree in Kelvin. Let's look at the units here. The kilograms per second all cancel out. The kilojoule per kilogram degree in Kelvin all cancel out. And I'm left over with a temperature of centigrade. I'm left over with a temperature of centigrade. That final temperature is 29.7 degrees C. That's the mixture temperature. 29.7 degrees C. So the mixture temperature, which is T3, is 29.7 degrees C. 29.7 degrees C. T mix, 29.7 degrees C. Inlet temperatures were 20 degrees C and 45 degrees C for the ethane and the methane, okay? Now, what if I were to give you just a little bit more information here? Not a lot. In fact, actually, I don't think I need to give you any information. What if I were interested in calculating the entropy generation? The entropy generation due to mixing. We suspect that mixing is irreversible because it's quite common to see smoke and air, so smoke and fresh air mixed together, but we don't ever see smoky air separate out into smoke and clean air. We don't see that happen spontaneously. We don't see a mixture of ethane and methane spontaneously separate out into two separate streams. That just does not happen in the real world. Therefore, one suspects that this mixing process is irreversible, and therefore S dot gen is positive. One suspects. One suspects. So let me write out the entropy balance for an open system for multiple chemical species. Let me write that out for you. And then we will proceed to solve this problem and determine what S dot gen is for this particular problem. So let me write down the entropy balance for an open system. So now I'm interested in calculating the entropy generation due to mixing. Mixing, you will see, is irreversible, okay? So what about the S balance? This is for an open system. Open system. Running out of chalk here. Let's see here. Here we go. So it looks just like the entropy balance for a single component system. So we got the sum of Q dot over the interaction temperature is equal to the time rate of change in entropy within my control volume plus the sum, double sum, over all species I, M dot I, SI, summed over all outlets, minus the same thing, sum over all species, M dot I, SI, summed over all inlets. Okay. The double sum there, the inner sum is for sum over all components. Component sum. That's what this second sum is for, okay? Now for this problem, let's go back to the problem here. Steady state, adiabatic. So two terms go away immediately in the entropy balance. Oh, I forgot the S dot gen. Minus S dot gen. Sorry about that. That's what we want to find. So we want to find S dot gen due to mixing. S dot gen due to the mixing. That's what we want to find, okay? So no heat transfer, so there's no entropy transfer due to a heat interaction. There's no change in entropy within the control volume at steady state. Let's attack these summations here. I have one outlet, but I got two species flowing across the outlet. So I have M dot C2H6, S of the C2H6, evaluated at the outlet, location 3, plus M dot CH4 times S CH4, evaluated at the outlet. Okay, and then I got two inlets. So I get M dot C2H6 times the specific entropy of the C2H6 evaluated at location 1 plus M dot CH4 S CH4 evaluated at the inlet location number 2. Okay? So that means 0 equals, let me group terms together in terms of mass flow rates. M dot C2H6 delta S of the C2H6 as I go from state 1 to state 3 plus M dot CH4 as I go delta S of the CH4 as I go from state 2 to state 3. Oh, and I forgot the S gen. Minus S dot gen. Let's put the S dot gen over on the other side of the equation. That's what we're looking for. S dot gen equals that stuff. Okay? Equals that stuff. Okay, so I need to find the change in specific entropy of the ethane and the methane as I go from their inlet to the outlet. Okay, from their inlets to the outlets. Well, let's do that. Let's do one here. Let's see here. Delta S of the ethane, C2H6, as I go from inlet port number 1 to the outlet mixture port number 3, assuming constant specific heats, is going to be equal to Cp of the C2H6 ln T3 over T1 minus R for the C2H6, and that's going to be natural log of P3 over P1. Now, R for the CH4, that's going to be equal to the universal gas constant divided by the molecular weight of the C2H6, the ethane. And I can look the molecular weight up in a table. That's no biggie. I can do that. I know T3 and I know T1. I know all the temperatures for the mixing process. What's this thing? What's this P3 over P1 all about? So what's this P3 over P1? P3 over P1. And remember, well, P3 over P1. What is this thing? Now, we got to be really careful here. This is the change in entropy, specific entropy of one component. It's not the overall gas, it's one component. So these are component pressures. These are component or partial pressures, okay? Now let's look at our device here. Let's look at our device here for a minute. Let's look at our device. So the ethane comes in at some pressure. I don't know what that pressure is, but I do know the mixing process is isobaric. So what this means is, if it's isobaric, what that means is P1 equals P mix, and P2 equals the mixture pressure at the outlet, okay? Now the partial pressure of each component at the outlet from, let's see, from what? How do we calculate the partial pressure here of each component at the outlet? Partial pressure of component I is equal to the mole fraction times P mix. So the component pressures at the outlet, the component pressures, P of the CH4 at the outlet is equal to the mixture partial pressure at the outlet times the mole fraction of the CH4 at the outlet. Okay, and the partial pressure for the C2H6 at the outlet is equal to the mixture pressure at the outlet times the mole fraction of the CH4, okay? So this ratio, P3 over P4, is the partial pressure of the ethane at the outlet divided by the pressure at the inlet. Now we're told that P1 is isobaric, so P1 is equal to P mix. It's an isobaric process. So in this case, P1 is equal to P mix. P1 is P mix. And the partial pressure for the ethane at the outlet is P mix divided times the mole fraction of ethane at the outlet. So this guy here is YC2H6 at the outlet times the mixture pressure at the outlet, okay? Okay, so let's write what we have here. Oh boy. So I get YC2H6, and this is at the outlet, P mix over P mix. P mixes cancel out, and I get the mole fraction of the ethane at the outlet. Let me make sure my nomenclature is reasonable here. So let me write mole fraction, just to make it clear. This is at the outlet right here. This is at the outlet right here, okay? So surround it, put some trees there, okay? Okay, so this term here becomes the mole fraction of my C2H6 at the outlet. Okay, it's my mole fraction. In other words, it is N dot C2H6 at the outlet divided by N dot mixture. A mole fraction can be written in terms of a mole flow rate as well as moles, okay? Okay. Now, I got a couple of things to calculate here. I have the temperatures, I have the CPs, the molecular weight. Oh, what's the molecular weight for my molecular weight for the C2H6? I can look that up in the table. Let's get that out of the way. Molecular weight for the C2H6. Let's see here. Molecular weight. C2H6, 30.07, that's the molecular weight. 30.07, so that's no biggie. 30.07 kilograms per kilomole of ethane, okay? So check, I got this. Gas constant, 8.314 kilojoule per kilogram degree in Kelvin. That's no biggie. So now I need to find these mole fractions here. I need to find these mole fractions. And the mole fraction flow rate. Well, so we know the mass flow rates. We know the mass flow rates. So here, oh, there we go. So we know the various mass flow rates here. So now we want to get the mole flow rates, or the ratio of the mole flow rates. Let's do that. Well, N dot mix, that's going to be equal to the mass flow rate of the C2H6 times divided by the molecular weight of the C2H6. This will be N dot, N dot mix is equal to N dot C2H6 plus N dot, this is at the outlet, CH4, which is equal to M dot C2H6 divided by the molecular weight of C2H6 plus M dot CH4 divided by the molecular weight of CH4. The molecular weight of methane, let's get that one too. Let's get that one too. We should be in good shape here. Molecular weight of methane. Molecular weight of methane, 16.04. 16.04. 16.04 kilograms per kilomole. Okay. Notice the unit here for these fractions are kilogram per kilogram per kilomole. The kilomole goes upstairs and we will get kilomoles back. I know all these mass flow rates. Let's see here. It's 9 kilograms. 9 kilograms per second. And then I'm going to divide it by the molecular weight, 30.07 kilograms per kilomole. That's for the ethane. And then I got 4.5 kilograms per second. And then I have 16.04 kilograms per kilomole. The kilograms cancel out. And I get kilomoles per second. Kilomoles per second. So let's find the mole flow rate for the mixture. Where's the mole flow rate for the mixture? Hope I have my calculator. And I get 0.5813 kilomoles per second. 0.5813 kilomoles per second, okay? So that's N dot mix. That's N dot mix. What's N dot for the ethane? So I got N dot mix at the outlet is 0.5813 kilomoles per second. What is N dot of the C2H6 at the outlet? Well, that's going to be here. This is for the ethane, so 9 divided by 30.07. And I get 0.29. 9 kilomoles per second, okay? Okay, so let's plug in specific heat for the ethane, 1.766. 1.766 kilojoule per kilogram degree in Kelvin. Natural log, T3, the outlet temperature was 29.7. Oh, needs to be in Kelvin. Needs to be in Kelvin, so 273 plus 29.7. 29.7 plus 273. That's the outlet temperature. That's the outlet temperature, T3. And the inlet temperature for the ethane was 20 degrees C. And of course, I got to add 273 onto that to get it in Kelvin. So 20 degrees, 20 plus 273. And now I have minus RU, which is 8.314 kilojoules per kilomole degree in Kelvin. divided by the molecular weight for the ethane. So that is 30.07 kilograms per kilomole. Kilomoles cancel out and I get kilojoules per kilogram. And then I have the natural log of n dot for the ethane, 0.299 over n dot for the mixture, 0.5813 kilomoles per second. And I get a total change in enthalpy. Let me get this here in a second. What's the total change in entropy for the I get 0.24 kilojoule per kilogram degree in Kelvin. 0.247 kilojoule per kilogram degree in Kelvin. That's delta S of the C2H6 from 1 to 3. That's from 1 to 3. I'm sorry, 0.240, not 7. Sorry about that. We go through and we do the same thing for the methane. Same procedure, CH4 from 2 to 3. Go through the same exact procedure. Calculate the ratio of the pressures, the partial pressures for the methane. And I get 0.265. 0.265 kilojoule per kilogram degree in Kelvin. Okay? All right, we have the mass flow rates, we have the delta S's. Let's plug in. Mass flow rate for the ethane, 9 kilograms per second. Delta S for the ethane is 0.240 kilojoule per kilogram degree in Kelvin, plus m dot for the CH4, which is 4.5 kilograms per second, 4.5 kilograms per second, times delta S for the methane, 0.265 kilojoules per kilogram degree in Kelvin. Kilograms cancel out, and I get kilojoule per degree Kelvin per second. And I get S dot gen. What's my S dot gen here? S dot gen is 3.353. 3.353 kilowatts per degree Kelvin. So S dot gen. S dot gen. Inside of here, during the mixing process, S dot gen is 3.35 kilowatts per degree Kelvin. Positive or negative or zero? Obviously, it's positive. So note, S dot gen is positive. S dot gen, 3.35 kilowatts per degree Kelvin. Let's put a box around it. Notice that it is greater than 0. Hence, it is irreversible. Okay? It's spontaneous and irreversible. Gases mixed together, no problem. They don't spontaneously separate themselves apart. If you were to reverse this problem, make this the inlet, make these the outlet, and you were to, on the board, separate the mixture, spontaneously separate the mixture, you'd go through and you do the calculation on S dot gen, and you would get a negative 3.35 kilowatts per Kelvin. That is impossible. So mixing of gases is irreversible. It occurs in one direction only. You have to do work to separate gases. You can't have isobaric, adiabatic, no work separation. This mixing process is irreversible, spontaneous, occurs in nature naturally. The reverse does not happen. To separate this mixture into its two components, you have to do work. Okay, that's not the same problem we have here, but I'd have to do work to separate out the gases. Okay? All right. Take care, ladies and gentlemen.